Okay, in this problem we have the fare F in dollars and the distance D for two different companies for the trips they run. This is the charges, right? We want to know for transcontinental how many miles is a trip that costs $99. So we're going to use the graph here as a basis for an estimation in algebra, and then we're going to find the precise value in algebra. So for transcontinental, right, we have this long x-axis here representing what? Well, representing distance, and the y-axis is going to be representing cost. So if we set up what we know that with this formula it's 0.15 right up here. F equals 0.15 times the distance plus 12. So even say of a little table, we can see how this might work. If the distance is 0, 1, or 2, let's say, and then, right, we do want to know what's going to happen at 99. We'll get there in a moment. So what is the fare? So if the distance is 0, the fare is 0. The distance is 1, we have $12. Oops, sorry. If the distance is 0, the fare is 12, right? Because 0 times 0.15 is 0, plus 12 is 12. There's a starting cost here. You have to pay $12 up front. And then you add 15 cents per distance of mile per mile after that. So if we go 1 mile, it's 12.15. 2 miles is 12.30. What would 99 miles be? Well, let's go for that. If we had, right, let's say it would be equal to 0.15 times 99 plus 12. There are many ways to do this. I'm just going to do the long multiplication. Right, this is 0.15 times 99. We get 5, 4, 45, and 4 is 49, right? Placeholder 9, 9, add them up. And what do we get? Oh, 5, 18, 13, 14. So we should get 14.85, then plus 12. So clear that off, 14.85 plus 12, that equals 26.85. And I guess, that was using the algebra there to get the exact value, but I don't know, we had it right there, so I went for it. For distance, we're looking at from 1 up into 99. So I'm going to go by 5. Let's say 5, 10, 15, right, 20, and so forth. It's 30, right, 40, 40, 50, 60, 70, 80, 90, and 100. Okay, so here, those are our distances. Now the cost, let's go up by, let's say, I don't know, by 2s. 2, 4, 6, 8, 10, 12, 14, 16, 18, 21, 22, 24. So 2, 4, 6, 8, 10, 12, right there. 14, 16, 18, 20, 22, 24. I would normally label all the hash marks, especially if I had graph paper, but it's a little bit difficult here. Now when we're at 0, right, we're at 12, so that's our starting point. And then if, I can extend this line. Now we know the line's supposed to go about, let's say, here. You can see why that makes sense, because early on, even at 5 days, we still haven't passed $12 yet in cost. So of 5 miles, we haven't got above $12 in cost. So this line models what we predict would happen here, right, with our equation, what the algebra shows. And you might label it y equals 0.15d plus 12. The point is you can use this graph to estimate, but if you need a precise number, it's probably a good idea to use the algebra. The same is true for the next one for intercity express. The equation is a little bit different, and maybe I can use the same graph. Oh wait, but they're not even asking that, sorry. They're asking a different question here. For intercity express, how far can a person travel for a fare that is at most $99? So okay, we have a different function, f of x, well, I'll just write f for fare, equals $5 plus 0.2 times d. And they're saying, let's say the fare is at the very least, so anything less than or equal to $99, what values can we have for D? So what distances? Well, let's solve, right? Plug in 99 for F, right? And we know that if we plug that in, if we solve for D, that will be the maximum value we could use, right? So here, subtract 5 from both sides, and what do we get? Well, if we subtract 5 here, we get 94 equals 0.2D divided by 0.2 on both sides. This cancels out. 2 is 2/10, so here D is equal to 94 divided by 2/10. That really equals 94 times 10 over 2. But to quicken this up, these cancel out. It's 47 times 10, so D equals 470 miles. That is when it equals $99. So D could be anything less than or equal to 470 miles, right? And that would be our answer there. Anything more than that, and you would pay more than $99. Now we can confirm this with a graph, right? If we use the same graph as well, it's fine. Here, if we graph this line, it's a little bit different, right? But the rate will also show cost here over time. Anyway, so the problem is, of course, let me just stress this part, is that the distance is 470 miles, 4 times longer than the width of this graph. So I guess we do need a new graph. So I'll just clear this graph off and just rescale it. So you can see that this graph is actually representing what our algebra is predicting. So we set up the axes, right? We have distance, and there's our y-axis right there. So now we know that at 0, right, it's at 5. That's our y-intercept, and then it's $0.2 after that. So here, if we go up by, let's say, 5s, 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. Well, I want to go by tens because we need to reach $199. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And then we have our miles, right? 1 and then 2, 3, 4, let's say 5 is about here, right? 10, 15, 20, 25, 30. Oh, sorry. Again, we need to reach all the way to 470. There's no point in using ones. Let's go by 20s here. So, and our scales are not even. 20, 40, 60, 80, 100. 20, 40, 60, 80, 200. 20, 40, 60, 80, 300. And 20, 40, 60, 80, 400. 20, 40, 60, 80, 400. 420, 400. 40, 460, 480, 500. Okay. So even with a graph that covers this large of a domain and range, we can quickly graph. So the y-intercept's at 5, so about here, and then $0.2 past that. So you can imagine that at $20, where would you be? Well, 20 times 0.2, it's equal to what? Well, 0.2 is 2/10. Times 20 is equal to $4, plus the 5 is $9. So at 20, we're here in height, about $20, and then at $9. At 100, right, 100 times 0.2 is 20, plus 5, we're at 25. So at 100 here, we're at 25. So you can see I'm kind of estimating where the line should go. And if you keep that line in continuous direction, even with this rough and terrible of a scale, you get a good approximation that at about 480, right, or 475 or so, like right here, you hit about $99. Pretty close, right, to the actual approximation here. So that graph can be done. You just need to really kind of set where the line should be with some keystone input values. Okay, now they want to know one last thing. Is there a distance to which the fare of the two bus lines is the same? Well, yes, and you can think about this intuitively as well, right? For the other line, we start off at a higher amount, but have a slower rate. So unless the rates are the same, which would mean they're parallel, they're going to cross somewhere. So here, again, we're starting at 12, but then our rate of increase right, is pretty slow. So it's not costing as much per mile. So we have some indicators I'll just point up here. We know that after 99 miles, you'd be at about $27. So here's 10, 27's about here. So actually, I want to say the crossing point is somewhere around 100 miles. But there is no need to guess because all you have to do to solve that is set the equations equal to each other. So 0.15d, and that's just finding, you're saying, okay, let me set them equal to each other and find when that distance is. So it's 0.15d plus 12 equals 5 plus 0.2d, right, 0.2d, or 0.20d, same thing. So here, what we're going to do is subtract 5 from both sides and subtract 0.15d from both sides. And this puts my variables on one side because this cancels out. This is 7, this cancels out, and this equals 0.05d. And then d equals what? Well, it equals 7 divided by 0.05, and 0.05 is just 5 out of 100, or we can reduce that to 1 over 20. You multiply by the reciprocal, and then d, if we work that out, d equals 7 times 20 over 1, so it's 140 over 1. Not bad. So 140 miles. Right, here's 100, 110 about. On my graph, a little bit off, they do meet. So you can use the graph to approximate the equation. The better your graph, especially if you're using graph paper, the better your approximation will be. All right, hope this helped.